Students, today we can continue our topic of physics, that is system of particles and rotational motion. Okay, so today we are going to learn about the equilibrium of rigid bodies. Okay, what is the name of the topic? Equilibrium of rigid bodies. So what is exactly equilibrium of rigid bodies? So you have the idea about the rigid bodies. Rigid body means the body in which the distance between two particles does not change under the action of applied force. Okay, means when you are applying some force to that body, then at that time distance between the two particles do not change. So that is called as the rigid body. But we want to learn the equilibrium of rigid body. You know what is equilibrium? Equilibrium means summation of all the forces acting on the body. If it is zero, that time we can say that this body is in a equilibrium position. Now my point is equilibrium of rigid bodies. Okay, so now means when that rigid body moves, then at that time it has two types of motion. One is the translatory equilibrium motion and second is rotational equilibrium motion. Means these are the two types of motions are there for that rigid bodies. So what is the exactly meaning of that two statement? Now you see here, first equilibrium, that is translational equilibrium, okay, and second is rotational equilibrium, rotational equilibrium position. Sir, what is the meaning of that two statement? Means when that rigid body moves, then at that time its linear momentum and angular momentum of the body should be remains the constant. Okay, it should be remains constant. That is the meaning of equilibrium of rigid bodies. Linear momentum means it is related with the translational motion, and angular momentum which is related with the rotational equilibrium. So what is the exactly meaning of translational equilibrium? No doubt, translational equilibrium, again it has two types, that is the static equilibrium, and second is dynamic equilibrium. Okay, sir, what is the meaning of first of all translational equilibrium of that rigid body? Now the body is said to be in a translational equilibrium if summation of all the forces acting on the body is completely zero. Okay, so that is called as the translational equilibrium. Means if I want to explain that translational equilibrium, then summation of all the external force acting on the body should be zero. So that is the meaning of translational equilibrium condition. Okay, so sir, what is the exactly meaning of that statement? Means mass into acceleration vector of center of mass should be zero, or we can also say that m into dv by dt, that is center of mass, is equal to zero. Summation of all the forces acting on that body will be zero. Means m is equal to zero means derivative of VCM, okay, velocity of center of mass, derivative of which term is zero means velocity of center of mass should be remains constant. Okay, now velocity of center of mass should be remains constant means exactly the body should be continue in the same state of motion. If this body is in the rest position, then at that time we can say that body have the static equilibrium position. In the rest position, that is the static equilibrium condition, means velocity will be remains constant, that will be zero. And dynamic equilibrium means if the body is moving with uniform motion, then the body should continue into the same motion. So that is called as your dynamic equilibrium condition. Okay, so this is all about translational equilibrium. So then now question is, sir, what is exactly rotational equilibrium condition. Rotational equilibrium means we can say that a body is said to be in a rotational equilibrium condition if summation of all the torques means due to the force exerted on the body will be zero. Okay, means here in that case we can say that summation of all the torque externally which is acting on the body is zero. Okay, means that whatever the moment of force which are acting on the body in a different direction, that pair of forces cancelling the effect of each other, but the body will continue in the same state of rotational motion, then that is called as the rotational equilibrium position, okay, or condition. So that can also be written as, that is, torque external is zero, or torque can be written as force into perpendicular distance means R. Okay, force external into R acting on the body should be zero. So these are the condition of that your rotational equilibrium. In completing the equilibrium of rigid bodies, okay, so there are the two types of equilibrium, translational equilibrium and rotational equilibrium. Translation equilibrium is again your two types, so that is static and that is dynamic equilibrium. Now we can continue to the next point, that is equation of rotational motion. So you all learned the three kinematic equation for the linear motion. Similarly, there is an analogy for the rotational motion. Okay, so can you tell me which are the three equations which we have learned for the kinematic equation? So the first equation which we have learned in a linear motion, first of all, in a linear motion, you have learned the first kinematic equation. A linear motion, okay, kinematic equations are kinematic equation. So, first kinematic equation is V is equal to U plus AT. V is equal to U plus AT. So, similarly, here in a rotational motion, we have the three kinematic equation. So, here in that case, V is equal to U plus AT. V is the final velocity of the body. U is the initial velocity of the body. A is the acceleration produces into that body during the time t, that is t is the time taken to change that velocity. Okay, so that is the first equation. Similarly, in a rotational motion, there is an analogy of linear velocity and angular velocity. So therefore, if I will say this rotational motion omega is equal to omega 0 plus alpha into t, where omega is the final angular velocity, omega 0 is the initial angular velocity, alpha is the angular acceleration, and t is the time taken to change that angular velocity from omega 0 to omega. Okay, so that is the first kinematic equation in rotational motion. Okay, second equation in linear motion, second kinematic equation in linear motion is S is equal to ut plus half at square, that you have learned, where S is the displacement covered by the body, U is the initial velocity during the time t, t is the time taken, A is the linear acceleration, t is the time. So there the same equation in analogy we can say S means here angular displacement is equal to initial velocity omega 0, that is the angular velocity now here, plus half alpha into t square. So that will be the your second kinematic equation for the rotational motion, where that theta will be the angular displacement, omega 0 is the angular velocity, t is the time taken, 1/2, and alpha is the angular acceleration, and t square. And the third kinematic equation that we have learned, that is the v square. In linear motion we have learned v square is equal to u square plus 2 times as. Okay, and that equation can be calculated in a rotational motion is like this. So omega square is equal to omega 0 square plus 2 times alpha into theta, where omega square is the final angular velocity square, initial angular velocity square, alpha is the angular acceleration, and theta is the angular displacement. Okay, so you can take one sum on that, so that you will get the idea about how to use that equation. So question is like this. Okay, can I rub these things? Okay. So sum is like this. A constant torque of a magnitude, 500 Newton meter acting on a body increases its angular velocity from 4 radian per second, means omega 0 is 4 radian per second, to omega is equal to 20 radian per second. In 8 seconds, calculate the moment of inertia of the body about an axis of rotation. So now you see here, if you want to find out the I and you have the torque, tau, so then there is a relation of tau and I. Torque is equal to I into alpha. And if you want to find out I, so you need alpha. And for that alpha, we have a equation of first kinematic equation as alpha is equal to omega minus omega 0 upon t. Okay, so that is your alpha. And once you got that relation, then I will substitute the value of omega naught. Omega will be 20 radian per second, that is 4 radian per second, and time taken will be 8. Okay, so therefore that answer will be 16 by 8, that is equal to 2 radian per second square. And so as torque is equal to I into alpha, so I is equal to torque upon alpha. And the torque has been given to you, that is 500 divided by alpha will be 2. So therefore 500, okay, so 500 will be that is the torque. So therefore that answer will be 2 2s are 4, 2 5s are 250, 250. So that answer will be 250, and that is moment of inertia kg meter square. Okay, so that will be your right answer. Okay, so this is how we can calculate that any sum on that rotational motion. Okay, next time we can see the principle of parallel axis theorem and principle of perpendicular axis theorem. Okay, so that today we'll stop here, and tomorrow we can continue to that both the theorems. Okay.